Well, let's get started. Quick announcement. On Thursday, we have an exercise, so remember to bring your computer. There's a little bit of homework before this, problem 22 and 23, where problem 22 is basically an extension of what you did in problem 21. And the idea was here, problem 21, which we will discuss today. Problem 21 is a robot, translational joint, rotational joint. Version A, translational joint, rotational joint, translational joint, rotational joint. Version B, and you did that with pen and paper. And now we want to extend that to basically arbitrary long chains. That's kind of ridiculous for a robot, especially a planar one that has at max 3 degrees of freedom at the end effector. You can say a few degrees of redundancy are good to navigate maybe around obstacles, but this is ridiculous. Still, we want to do this as an exercise, and the idea here is that you write a little MATLAB program from scratch that does this computation. The idea is that you understand this idea of recursion and how to do something like this recursively or in a loop or however you want to do it before we implement it in the framework, because the framework in the end is going to feel like magic. We're putting together all the different pieces, the linked list, then we do the computations across the joins, then we do inheritance to get different joint types, and in the end it just fits together and works like magic. And it's kind of difficult to have then the overview of what is actually happening, because stuff is distributed across different objects, stuff is done in a recursive fashion, and so on. So this is a good exercise to set up, at least write an algorithm, a complete short algorithm that does this all at once for a very simple example. We will use this example later on to reason about efficiency, computational efficiency. So this n here, number of joint pairs, right, translational, rotational, at some point we will choose to be 1,000. So you get really a multi-articulated, hyper-articulated snake robot. And there's some interesting snake robots around, but none of them are basically fixed on a base and have an end effector, but then they sort of move, undulate through open terrain. So this would be problem 22, and in the usual fashion, right here, a few test cases that allow you to check whether your solution is correct. And then problem 23 is a reading exercise. So there's MATLAB documentation on how to do linked lists in object-oriented programming. Some of this we've already seen in class with a very simple example. This goes a little bit more into the details how to do this in object-oriented programming. So a reading exercise. And then on Thursday, we will set up our first true kinematics problem, where you can already see this is a robot with 3 degrees of freedom, 1, 2, 3 rotational joints, 3 bodies, and a triple pendulum. And ultimately, what we want to do is we want to run a nice animation. We haven't done dynamics yet, but I can give you a trajectory of joint angles, and the idea is then basically at every iteration, pick the joint angles from your file, update with an outward pass all the positions, orientations of your bodies, plot them, put them to the screen, and then you will get a nice animation if you did everything correct of your triple pendulum. Questions? No? Then in class, we talked about motions across a joint, right? When we talked about these algorithms, we said the joints have to do some, x of the successor is x of the predecessor plus some delta x. And we defined that a little bit cleaner what we mean. With x, position and orientation, position given by a vector from an inertial reference, expressed in the coordinates of the successor or predecessor respectively, and then rotations through a 3x3 transformation matrix. And we came up with basically these equations to get the motion across the joint, where a key idea was to have designated joint coordinate systems. We call them dp and ds. In MATLAB Simscape, they're called base and follower coordinate systems, which are sitting on the bodies, on the predecessor and the successor, but you think of them as something that belongs to the joint. Right? It basically tells the joint, where's the joint located in the predecessor body, where's the joint located in the successor body. And these notions of predecessor and successor are local to the joint. Right? This body here has probably another joint mounted here, and there's going to be a coordinate system, and in this case the coordinate system would then be called the dp system, right? Because for this joint, which is moving away from root, this body would be the predecessor of this joint, right? And then all the labels would change. So we have to think of this as a template that moves basically along our kinematic tree, and for every individual joint there's a predecessor and a successor, and due to this recursion we always know what the predecessor is doing. If we don't, we move one step closer to root. In the past, I had a very low-tech way of highlighting what these joint coordinate systems can do with old school transparency. So you can basically highlight where's your successor coordinate system, your ds coordinate system. I will just pass them around to show you how, or to let you play around with them. There's the example of a very simple joint that, depending on what you want to do, you can turn into a rotational joint or translational joint. Just play with this if you want, or pass it on if you don't. Here, this idea that using different coordinate systems, you can realize different joints. I put this here as well. And the last one is probably the most interesting one because it already goes into what we will do on Thursday. It models a rolling contact joint, where there's sort of this interesting question: where do you put your joint coordinate systems in a rolling contact joint? Can I borrow your bottle for a second? I need a rolling contact. Thank you, Toby. Where's the joint, right? If I have a motion like this, right? The point of contact, of course, is down here. But it turns out it's much easier to place the joint coordinate system in the center of the rotation. And this is basically what you will see on this last set of transparencies. There are my predecessor with a ground, and you have your successor, which has the little round circle. And you can play with that as well, just to get sort of a more intuitive understanding of what's going on. Questions? No? We left off with positions, right? And we derived these equations here sort of in closed form. It's pretty straightforward. The only thing that we have to take care of is that there are certain transformations, because things are always expressed in local body fixed coordinate systems. And then what I ended with in the last lecture is basically doing this in a sort of mini recursion, or in 3 steps, where I say I first compute the position of the origin of my dp system in dp coordinates, then the origin of the ds system in ds coordinates, and the position of the successor body in successor coordinates. It looks the same, almost the same, 3 times, with sort of a small difference. And I forgot to make this explicit last lecture, that of course this rotation across the joint, dp/ds, the relative orientation of predecessor and successor joint coordinate system, that depends on q, right? That is somehow influenced by the motion primitives within this joint, where we haven't really discussed in detail what they will be doing, but we saw this one simple example of a rotational joint, where here we had cosine of gamma, where gamma was basically our q value. And then the second difference of course, right here, stuff in red depends on Q, stuff in gray is body fixed, and then here we had sort of a change of signs, because simply things are always defined from the predecessor body going forward and from the successor body going backwards. So that's why I have a minus sign here, and we don't have a transpose here. But positions have been covered. So the next thing that I want to discuss are velocities. And I don't want to do this in the sense of now taking the position equations and taking derivatives, but directly thinking about physical velocities. And what I want to know in this first iteration step is I want to know the physical velocity of the dp origin, so the origin of the predecessor coordinate system. And that leave a little bit of space because we will need a coordinate transform afterwards. Of course, depends on the velocity of the predecessor coordinate system and on the velocity or the relative velocity between predecessor and successor coordinate system. And I would write that as the physical vector rp dp. This we will need in a second. This is basically the way I want to think about this, right? We have relative velocities, so the velocity of the dp system is the velocity of the p system plus the relative physical velocity between these two. Now, all I have to do now is to express this in coordinates. And again, we want to do sort of the same coordinates where dp vdp should be expressed in dp coordinates. The velocity of the predecessor is somehow given, right? That's something that we know recursively. We can always assume we know the velocity of the predecessor coordinate system. If not, back up through the tree until you hit root where you're absolutely certain know that the velocity is 0. And then rp dp, that velocity should also be expressed in p coordinates, sort of the same way we express this position, this relative position in p coordinates, right? The location of my coordinate system is given in predecessor coordinates. And then we see all that is missing is my a dp transformation. This should be gray. Okay? Yes, Chan, right? Tan.
Shouldn't Vp in p coordinates equal to 0, and Vp in dp is also 0 because it's a body fixed frame?
Yes. So this is, first of all, that's a good point, but that's different. When I say Vp, I mean the absolute velocity of body p against the inertial frame of reference, or if this point p, actually here I should talk about a point p. And that has some value if the body is moving, and has no value, 0, if the body is stationary. And now I can express this in p coordinates, I can express this in c coordinates, I can express this in I coordinates. That doesn't change basically the physical quantity. It's just different coordinate systems with different orientations. What you think is to say I have the relative velocity between point P and point P, right? And that, of course, is going to be 0. But this is not what we mean with Vp, right? Vp is the absolute velocity of point P. Has, first of all, as a physical quantity, nothing to do with the choice of coordinate system. And the choice of coordinate system is basically just an orientation or issue, right? In which, how is my coordinate system rotated in which I measure these quantities. Okay, I think that was a good point, good question. Others probably have the same doubt. Do you want to grab that chair right there? This is awkward. Do you remember this part where I told you that you think transport theorem is easy, and then when it comes up, no one will realize how horribly wrong this is?
A question about what does it mean, like the velocity r point is the rotation of the, it's like a cross product between r and the rotation of the dot.
So what's written there is wrong. Right? Because I said before, I want this physical velocity, which comes, of course, from the rotation of the body. Right? I have here my point B, here's my point dp, and then if the body rotates, this thing gets a velocity. Right? That is the physical velocity that we get here, the relative velocity between these 2 points. But just in principle, whenever I write down a physical derivative and express that in coordinates, I have to make sure I keep meaning physical derivative, because what I just wrote down was the notation for a numerical derivative. Right? Please keep that in mind. Right? Super important. Now, to connect these two, who can help me? So this doesn't change. This doesn't change, right? That is given. We know what this is. But what do I get back here?
Just the cross product between the,
What happens with the other term?
it's 0.
Oh, yeah. So we first would have the numerical derivative. So this is what I wrote before. And that guy, of course, is 0, because both coordinate systems are part of the same rigid body. Both points, both origins are part of the same rigid body. So the numerical derivative in P, right, in body fixed coordinates is 0. But then I get here my cross product, which in this case, my omega is the rotation of my coordinate system, which equals to the rotation of my body. And then I have rp dp in p coordinates. And this is basically the cross product, and that's exactly what we would expect, right? If I have, as I said, my body B, or my point B, if the point B is stationary, and here's my point dp, then dp will get some velocity if the body is rotating, right? Then this is rotating around an arc, and I get some velocity v dp. In principle, what we just derived is, is this still fundamentals? This, right? Exactly that equation. Velocity of some point q, here we call it dp, is the velocity of a point B plus that cross product, right? So points on a rigid body, exactly the same equation. Where are we? Here. With the only difference that after expressing this, we do an additional transformation in the dp system. Yeah? And note that I don't have to apply any transport theorem or any derivatives to this transformation matrix, AP-dp, because I already reasoned about velocities. That's why I did it this way. I thought about velocities, relative velocities are known, and then I just have to apply a transformation. Now I can continue that way. So the next step would be to get the velocity of the successor coordinate system. And there I have to apply the transformation A dp ds transposed, because now everything will be given in dp coordinates. Then I have the velocity of the dp origin, which we just computed, plus, and now I have to be a little bit more careful, because I have now r dot dp ds, right, which is given in dp coordinates. So the numerical derivative of the translation across the joint. And that one is now not constant, because the translation across a joint depends, of course, on the joint angle q, but the translational velocity that we have here depends on q and q dot. So if I have a translational joint that is moving, then it has some generalized velocity q dot, and that will lead to the fact that r dp ds is changing. Plus, back here, omega dp in dp coordinates multiplied with this original vector r dp ds. And of course, all of these red vectors depend on q and q dot and so on. I'll just, whenever I mention something for the first time, I try to make this dependency more explicit. Questions? An interesting point that's happening here is that we should think about a body as something physical. Sorry, a joint as something physical, bodily as well, but in this case, a joint as something physical. Yet, somehow the change of the joint here, I didn't write that as the physical derivative. Instead, I immediately expanded it. So what is left is basically just the numerical derivative across a joint. So how do the joint, the coordinates of this translation change in my dp coordinates? Just basically the numerical derivative. In a sense, a local view of the joint. Right? And that may be counterintuitive at first, because in principle we're always interested in a joint as something physical. So some of you may have expected to write it like this without expanding it. But once we did the expansion, we see that the joint by itself can never really know what the velocity, the physical velocity across the joint is, because it depends on the rotation of the predecessor body. That's simply, right, if I make another drawing, let's see if I have a good idea, right? So this would be now dp. This would be the displacement across the joint, and here would be ds. So this would be r dp ds, the displacement across the joint. And now you can imagine that this displacement it creates velocities in different ways. Number one, I change this vector here because the joint moves. For a pure translational joint, it would basically move ds that way, right? And this is what's covered here, right? The change within the joint. But then, of course, if this body is still rotating, right? We are still having all of this sitting basically on a predecessor that has some rotation. It means that that point ds is also moving. Right, and get some velocity this way. And that velocity, of course, depends on kind of both what's happening in the joint, how long is that distance, and what's happening in the body, how fast is the body rotating. So to basically get the physical relative velocity across the joint, I have to know what is the predecessor doing and what is happening in the joint. And this is why I want to focus here on the numerical derivative, which depends only on what's happening in the joint. Okay, questions? No? Then we repeat this, and the last step again is easy. Now we want the velocity of the successor in successor coordinates, and we have now the transformation a as ds without the transpose. We have as the physical velocity corresponding to this vector r I ds, we have the velocity v ds that we just computed. And now we have to subtract basically the counterpart of this, right? R S ds now comes in with a minus sign. And I expand this right away using the transport theorem. So we have minus rs ds, and that's already given in s coordinates, minus transport theorem omega s times rs ds expressed in s coordinates. And then this one here, right, the numerical derivative is again 0 because this vector rs ds is body fixed in s coordinates. Now, some of you may feel there's something missing because I always talked about how sort of a translational joint creates velocity. But what about a rotational joint that also creates some rotation here? Right? That would basically create a rotation here. And now I have my vector sds. And if I have some rotation here in the joint, right, the way we define things, it's translation first, then rotation. Right? If I have some rotation, again, I get some additional velocity component, which now depends on the rotation in the joint. And that doesn't show up explicitly yet. But you can imagine that this omega s here, that depends somehow on the rotation in the joint, because the rotation of the successor body depends on the rotation of the joint. And we will see that on the next page. Just something to keep in the back of your head, that this thing is reddish, right? Its value, the velocity of the successor, depends on q and q dot. Let's do accelerations next. And I want to do things a little bit quicker by focusing on the middle step, because we already saw when we get the middle step done, the first iteration is simpler because stuff is body fixed. The third is simpler because it's body fixed. So let's start here, right? The acceleration of the ds system expressed in ds coordinates. We will get stuff in dp coordinates, so we need this transformation adp ds transposed. Through the first step, we would get the acceleration of point dp, the origin of the dp system, in dp coordinates, plus. And now I basically need the physical derivative of this guy here, right? I need, in a sense, right, I've talked about acceleration, so I need the physical derivative of what's going here. The physical derivative of this, of vdp, is adp. Now I need the physical derivative of what's happening behind there. And to do that, right, I can immediately apply the transport theorem. So I will get basically the numerical derivative of everything that's written here, and then omega dp times that. So starting with the numerical derivative, the first term that I would get is r double dot dp ds, the translational acceleration across the joint, which now depends on q, q dot, and of course q double dot. Right? If my q dot changes, then I get some acceleration here. Then I have the second two terms where I get the product rule. So omega tilde dot dp and dp coordinates times r dp ds in dp coordinates plus omega dp tilde in dp coordinates times r dp ds dot. Again, this is expressed in dp coordinates. So this is the numerical derivative of what we had here. And now I have to apply the second part of the, or add the second part of the transport theorem, where we get terms that basically look like this, right? Omega tilde p times the original vector, and I can write this as r dp ds dot. Sorry, and this should be, of course, in dp coordinates. We will see in a second that this doesn't make a difference. And I can rewrite that a little bit. So I get my transformation AdPds transpose. I get the acceleration of the predecessor. I get the translational acceleration across the joint in dp coordinates. And then we can check. And I see that this term here, omega tilde times r dot, shows up twice. Comes here, and then I see it again down here. It's typical of Coriolis terms. So we get 2 times omega tilde dp in dp coordinates times the translational velocity. So here the product of a rotational velocity and a translational velocity. And then I have in front of my rdpds of this vector, I have omega dot from this equation up here, and here I have basically omega tilde times rdpds. So omega tilde squared. So here I get omega dot of the dp system plus omega, or omega tilde dot, and now omega tilde squared dp, and that gets multiplied with r dp ds. Again, in dp coordinates, close the brackets. Again, I can compare this to our equation of points on the same rigid body. And there we had acceleration of some point q. I'll get back to the other slide in a second. Acceleration of point q is acceleration of point b plus this term, where this is, in a sense, a centripetal acceleration, and this here is sort of the tangential acceleration. We discussed this in one of the previous homework examples. But this is already what you get if you have 2 points on the same body, right? And of course, that's what you have if you have a joint. Somehow there's a distance, and the predecessor is rotating, and that gives us an acceleration. So this is basically explaining what's happening here, and then, of course, what's happening here, right? Acceleration of point ds is acceleration of point dp plus this times this. This would even happen on a rigid body. And now we get 2 additional terms. Number 1 is the acceleration that comes within the translation of the joint. And of course, if this thing here is moving and is moving faster, it's going to create an acceleration here, right? The second one is a little bit harder to grasp, and we will look at a more a cleaner example a little bit later, but this is basically a Coriolis acceleration. And the way you can think about it is by saying, well, this guy here is a translational velocity, and So I'm somehow moving something along a line, right, within my joint. But that joint is sitting on a body that rotates with dp. So if I move along a line and at the same time rotate, the direction in which I move changes. Number one, also the radius in which I rotate changes. And this is basically giving me these two effects together give me this factor of 2. Don't worry about it too much. We will look at this in more detail later. This was the middle step. To compute this a dp in dp coordinates, right, corresponding sort of to this first step here, and then the acceleration of the successor, things are similar but simpler. Right, you would do exactly the same thing. You would just get different indices down here. But then you would see that, for example, this acceleration or this velocity r p dp dot, right, so which would correspond to this guy here, is 0, right, in p coordinates. And the acceleration r double dot between p and dp in p coordinates, this guy, would also be equal to 0. And then the same holds in the successor, so rs ds dot in successor coordinates is 0, and rs ds double dot in successor coordinates is also equal to 0. So there things simplify a little bit, and the expressions, I'm not going to write them down because they're going to be exactly this, just with these terms set to 0, or in other words, they're going to be simply the equations for accelerations of different points on the same body. Questions? Then let's talk about orientations. And this is something that we already derived, and we wrote this as a long product. Here, I just want to introduce again this mini recursion, where the orientation of the dp system is given by the orientation of the p system multiplied with this relative orientation ap dp. Then we have the orientation of the successor coordinate system of our joint, which is ai dp, orientation of the predecessor coordinate system, times a dp ds. And this is now a quantity that depends on q. So this is where we get motion if my joint variable, if my q changes, then through that process, ai ds will rotate against ai dp. And then last step, ais equals ai ds times as ds. And now I need a transposed corresponding to this minus sign. Right? So that's no big deal. We've seen this before. More interesting question now, what about angular velocities? And again, I don't want to go through the derivatives of transformation matrices, which may not get me to the result that I want here, but instead I want to think about this again as adding relative or adding angular velocities. So omega dp is the velocity of the angular velocity of the predecessor plus the relative velocity, I'll write this as omega p dp. Relative angular velocity between the p and the dp coordinate system. And then we can reason about in which coordinate system I want this. This is given in p coordinates. This here is, let's say it's given in p coordinates. And then I need to somehow do a coordinate transformation here. A, in gray, yeah, a p dp transposed. What can we simplify here? Say that again?
It's rigid body, so points.
There's no relative velocity, right? It's a rigid body. The b coordinate system, or the p coordinate system is fixed to the rigid body, and the dp coordinate system is fixed to the rigid body. So they always move together. So the relative velocity between these two is equal to 0. Right? That's simply because they're part of the same rigid body. So there we have no relative velocity. Now comes the next step, where we go to the ds system. And I want this in ds coordinates. And because of that, I already know I need some transformation matrix A dp ds transposed, written here in red because that, of course, depends on our joint angles q. Now I have omega dp in dp coordinates, which is, as we see here, right, the same as omega p in dp coordinates. It's basically just a coordinate transformation that we applied. And now I have this relative angular velocity between the dp system and the ds system, which I express in dp coordinates. And that is now not 0, because there's a joint in between, and that joint has some joint angle q, and if that joint angle changes and it's a rotational joint, we will get some relative angular velocity between these two bodies. So that depends then on q and q dot. And then I'm going to skip the third part because you already see, right, the same thing will happen again. If I know how the ds system is rotating, the s system will have exactly the same rotational velocity, just expressed in a different coordinate system. No surprises here. I think everyone would expect that, right? That my successor rotates if the predecessor rotates, and my successor rotates if the joint does some rotation. Angular accelerations. So I want to have this angular acceleration of the dp system, which will be given by the angular acceleration of the p system plus, well, the angular relative acceleration. I will write that as a 0, because we already know, right, this is not going to have any relative angular acceleration. Now I want to express this in dp coordinates, and I want to express this in, or this is given in predecessor coordinates, so all I need is to add a transformation matrix ap dp transposed. come on. Shouldn't I mean this? And I mean, in your defense, what I wrote was not wrong, because we, if I would expand this here, I would get omega p dot in sort of the numerical derivative, so omega p in p coordinates dot, plus now the transport theorem, which is omega tilde in p times omega in p coordinates. And that term back here is equal to 0. So because of that, it would be actually correct to write omega dot dp without the parentheses. And we discussed this briefly when we talked about angular accelerations. That we say, right, for physical for translational derivatives, we have a special symbol for acceleration to make very clear that there's a difference between, or let's say here, a velocity and a change in the numbers. With this, we mean physical derivative. With this, we mean physical derivative. For rotations, we didn't introduce a new symbol for the physical derivative, because we saw that the physical and the numerical derivative are the same. But that's only for this particular exception, where I can get rid of this physical, of the additional term through the transport theorem, because we're rotating, or the coordinate system that we express everything is rotating about this omega vector. So everything changes, but the omega vector stays constant, right? So this would be equally correct. This is how I will write it. But please keep that in the back of your head, that you cannot always do this, right? That this would be the correct way of writing things. And then once you expand, you would see that this is the same as the numerical derivative. I do the same now for the ds system, where we have, there's physical velocity, and now we have a dp ds transposed. And I have omega dp in dp coordinates, meant here physical derivative written as a numerical derivative because they are the same. But now I need the derivative of this guy, right? The physical derivative of the velocity across the joint, which I get through a numerical derivative, omega dot dp ds. And this is basically coming from the internal motion of the joint, in particular the internal acceleration of the joint, which depends on some q double dot, expressed in dp coordinates, plus I have omega dp times the angular rate. So omega dp ds of the dp system. Just briefly thinking about this, right? Acceleration of the successor coordinate system, of course, if the predecessor coordinate system is accelerated, there's going to be an acceleration. If there's some acceleration across the joint, right? If you think of this as a rotational joint and the joint is spinning faster, of course I will get some acceleration of the successor. Who can explain this guy? Right? The product now of two angular velocities. How does that create an angular acceleration? So I have a product of two angular velocities, and it gives me an angular acceleration. What's the intuition behind that? So let's think about my upper arm as the DP system and my lower arm as the DS system. And I have a joint here. And that joint, if I hold my upper arm steady, will create an angular velocity like this. Sorry. Let's do it this way, then I can do a right-hand rule. Right? So steady, moving here, I get an angular velocity this way. Right? So the angular velocity, if I just keep that steady and I have a steady angular velocity at my joint, right? Some steady q dot, no q double dot, just steady, gives me an angular velocity this way. Now I add an additional velocity to the angular velocity to the DP system, and I will do this. Right? So again, positive angular velocity. So my DP system is rotating. That means that if I now combine both things, and this is what we're doing, right? We're doing a steady velocity here and a steady velocity here. What will happen is that this angular velocity vector, this axis, is slowly rotating. Right? So I have here an angular velocity vector that comes from the fact that I'm rotating here. And now, because I'm also rotating here, that angular velocity vector is rotating. And then, of course, this is not the angular velocity of dp, because I would still have some component in this way, because I have this rotation. But in a sense, I'm doing this. And so I have an angular velocity vector that is rotating. And sort of that means there's some angular acceleration pushing down, right? So here we have, in a sense, one motion around an axis and another motion that rotates that axis. And that leads to an angular acceleration. Yes, question?
Will there only be an acceleration if the axes are different from each other?
If they're collinear, you wouldn't see that effect. Yeah. And mathematically, the cross product would evaluate to 0. Yeah. And physically, you're rotating a joint axis about itself, so it doesn't change anything. OK? Other questions? I will not write down the last step, because you can imagine it's the same that we saw up here, right? DS system and S system are sitting on the same rigid body, so they will have the same angular acceleration. Quick questions? No. So, in summary, what we can do is, if we know what's happening with the predecessor in terms of positions, orientations, velocities, accelerations, we can compute the same quantities in a successor, knowing what's going on joint level in terms of numerical derivatives in the joint. So local, right? We're not talking about physical velocities across the joint. We can't compute those because they depend on what is the predecessor body doing. But we can do sort of the local change, the numerical change within, or we know the numerical change within the joint. And with this, we now can go ahead and express positions, velocity, and orientations. And I'm going back to our X notation, where we wrote all of this a little bit more general, where we said if we have scleronomic constraints, we have a constraint function, and then I can compute velocities through my Jacobian, and I can compute accelerations sort of through this equation. And we saw this for scleronomic joints. We saw this for rheonomic joints, where I would get an additional term here, right, in the velocities. This is something I would call a bias velocity. Bias velocity means even though I have no q dot, there we go. Even though I have no q dot, I have some velocity in x. I don't have that in scleronomic systems. If I set q dot to 0, the joint is the system is not going to move, right? Something that comes from the time dependency. I have the same for non-holonomic constraints, where the only thing I changed is that instead of q dot, I write alpha, but I get sort of the same linear structure. If I look at everything on acceleration level, I basically see that this linearity is partly conserved. So accelerations are linear in q double dot through the same Jacobian. And then I have something back here, which I would also call a bias acceleration. So this thing here corresponds to the sigma here, which somehow depends on q and q dot. And this is what I will call a bias acceleration. With the same idea that I don't have, if I don't have a q double dot, so my joint velocities are constant, I have no acceleration in the joint, this term back here, the bias acceleration, would still give me some acceleration in x. And that is coming from this weird mix of joint velocity and changing constraints. So I have some motion, and then I have also some change in the constraints. And by putting these two together, somehow joint axes move around, directions of motion change. And even though the q dots are constant, this can lead to accelerations. If I have a scleronomic constraint, this bias acceleration still exists, but it gets a little bit more complicated because here my bias acceleration now also includes basically the direct time derivatives. And there's also a mistake in your template because, of course, now we get a direct time dependency of the Jacobian and these bias accelerations. But without going into the details, right now I have the same term I have over here, but I also have the direct time derivative or the partial derivative of my constraints against time. I still get, in the end, something that I will call a bias acceleration, with the idea that if q double dot is 0, I still get some acceleration. And of course, the same for non-holonomic constraints, where these bias accelerations will have a different form. That means for us, if we think about computing now accelerations, computing this in a structured way, and that's going to be very important down the road, is that we want this linearity. We want a linear relationship between q double dot and x double dot. We need that to do dynamics. We somehow need to compute Jacobians, and we still need to find a way to compute these bias accelerations, sigma. And we will get there in a second, and we will actually, don't worry about scleronomic and rheonomic and non-holonomic constraints. We simply will postulate that we will have a structure like this. Right? That's the important bit. We will always have some structure where velocities, accelerations are linear and joint accelerations, and there's some bias term. Now, here, I very carefully expressed everything in inertial coordinates to avoid any influence of moving coordinate systems. But we could do this, the same thing, of course, in body fixed coordinates. So if I would like to have the acceleration of a point B in body fixed coordinates, and note how I very carefully wrote this as a, with parentheses, as a physical derivative. Right? And this is what we mean when we say A, what we said before, AB, the acceleration of body B in B coordinates. Well, I can write that as ABI times the same quantity expressed in I coordinates. And then in I coordinates, I can, in a sense, replace or remove the parentheses, right? That's the second exception. Once I'm in inertial coordinates, numerical and physical derivative are the same. If I could still apply the transport theorem, but then the rotational velocity of the coordinate system would be 0, so it wouldn't contribute. And now I can write this as ABI times, and this x, right, that we've expressed in I coordinates before, I can write this as JF times Q. Q double dot plus, of course, there's some, again, some bias acceleration that we get through the sigma b. And now I can go ahead and give this here a name. And I will call this the Jacobian of body B. And this will be the translational Jacobian, hence the S. Translational, I don't want to write a T, because then you think it's a transpose. And I will state that that Jacobian is expressed in B coordinates. And back here, I will also say that this bias acceleration is expressed in B coordinates, and we'll call it S. So the same structure should now hold for motions of our body. Here just written for translational motion for simplicity, where I say the acceleration of a body B is this translational Jacobian times the generalized acceleration plus some bias term, right, which is a vector expressed in B coordinates. And here we're talking about the translational bias acceleration, so that's where we get an S. And in a similar way, we could write the velocity of some body B as the Jacobian, same Jacobian, exact same Jacobian of this body B times Q dot, plus potentially some direct time derivative that we would see in dt, partial t, in scleronomic joints. So this doesn't always show up. But we have sort of this linearity that will be very important between our generalized coordinates and our Cartesian coordinates. And this directly applies to the representation of this x, right, that we now defined, where we said x is this position vector RIB in this case, and then here are its derivatives. I'm showing this because here it's a little bit important to note that my JBS in B coordinates is not the same as partial RIB in B coordinates partial Q. Those two are not the same. Simply because partial RIB in B coordinates partial Q times Q dot is going to give us the numerical derivative. So RIB in B coordinates dot, right? This is going to be the numerical derivative of this vector RIB. Right? This is here, I'm just applying a numerical differentiation rule, right? If I take this numerical derivative and say, hey, compute this, you say, oh, that somehow depends on Q, and then Q has a time derivative. So you would just numerically arrive at this equation. And that, of course, is not the same as the velocity of body B in B coordinates, which is RIB dot in B coordinates. So the physical derivative in B coordinates, and the two again translate connected to through the transport theorem. And this is what we want when we say JBS be in multiplied with q dot. So subtle but important difference, where this definition of the Jacobian also somehow includes the motion of my joint coordinate system, and hence gives me a physical derivative, whereas sort of this partial derivative of my numerical position vector would only give me a numerical derivative. Not too much to worry about right now, because in the next lecture on Tuesday, we will define another way of computing this Jacobian, right? Again, through a recursion. We will simply postulate, hey, somehow there's going to be a structure like this. And we know it for the predecessor. In particular, we know it for root, because for root, that Jacobian is just a bunch of zeros. So we can always make the assumption we know it for the predecessor, and then the question is, can we recursively compute a similar Jacobian or Jacobian with the same structure for the successor? So we will never have to go through partial derivatives or even go through these constraint functions or these vectors R. But in general, we already see that the Jacobians will become important. It's not enough to simply compute positions, accelerations, and velocities, as we've done so far. We also somehow want to get these Jacobians and these bias accelerations, because they preserve structure. There's a linear relationship that we see here between the acceleration of a body and the accelerations in the joints. And we will need these structures when we do when we do dynamics. What I want to do today for the rest of this class is hence going back to talking about Jacobians. And this is here your problem 21 that was given as homework. And I just want to discuss what was going on, right? You have here two simple robots, translation, rotation, joint, and then here's your end effector. And everything is planar, and in this case we simplified our axes to say they're basically in position, x and y coordinates, and an orientation. And here we have two bodies, and the position is given sort of here at the end effector and here at the end of this first link. And here I have three bodies, 1, 2, and end effector. And again, the positions are always given at the end of each of these links. And your homework was to basically compute the the explicit constraint functions fc for case A and for case B, and then compute the Jacobians. And those are the results for the Jacobian computation. And I want to show you how to read such a Jacobian again. And the important thing here is to first of all identify a block structure. I have in a Jacobian multiple columns, and each column is associated with a joint velocity. The first column, right, in the end, we have this equation x dot equals Jacobian times q dot. So each column will be multiplied with a particular velocity. The first column with q1 dot, the second with q2 dot. That's the structure in the columns. Every row corresponds to an entry in x, which means here we get two blocks where the top block would be corresponding to this first link, P1, with x coordinate, y coordinate, orientation gamma. The second block would correspond to the end effector, again with x, y, and gamma. And these are the coordinates, but we should think about them again as sort of velocities, right? Because if I multiply q dot with this Jacobian, I get here the corresponding velocities. Same down here, right? Each column of the Jacobian corresponds to a Q. Here I have Q1, Q2, Q3, Q4. So 4 of them. And then each row corresponds to some degree of freedom in X. And here we have 3 bodies. So again, I can do this as blocks. The first one would be body 1, body 2, and the end effector. And sort of same idea. Translation to the right, translation vertically upwards, and rotation. Okay, that is the first thing if you look at a Jacobian, how you should read it. And we will later stack Jacobians on top of each other and we'll separate them. And if I ask you basically what's the Jacobian of this body P1, you would see immediately that's just the first 3 rows. Right? If I'm just interested in the motion of the end effector, I could just take the Jacobian and extract the bottom 3 rows, and I would get the information about the end effector. Now, what we see here are the directions in which we can move. So, body 1, P1, has here a direction that corresponds to Q1, and that direction is 0 to the right, 1 upwards, and no rotation. So this would simply be moving straight up. And that makes sense, right? Because if I look at this joint Q1, all it does is it moves up and down. So this point P1 can only move up and down. I see the same entry down here with PE, because if I have some motion, right, some translational motion about joint Q1, all it's going to do is move straight up and down with exactly the same velocity. So if I look at the first column of this Jacobian, right, I get the motion if Q1 moves and all the other joints are blocked. And if all the other joints, so in this case Q2, are blocked, then this whole arm is just going to move straight up and down. P1 and PE will have the same velocity here, shown just 2-dimensionally, but in this case we also don't have any rotation. So this would be the red arrows. Blue arrows. If I do a motion about Q2, what is that going to do with this body P1? Nothing. Nothing, right? Because the joint sits further away from root than body P1, and that's reflected here by this bunch of zeros. And in general, in these Jacobians, we see sort of a triangular structure of these zeros. We see this even more pronounced down here, where P1 is only influenced by Q1, and Q2, 3, and 4 are not going to move it. So there's going to be zeros in the Jacobian. This body 2 is only going to be influenced by the motion of Q1, Q2, and Q3, the joints connecting it to ground, to root, whereas Q4 is not going to move P2, again reflected by a bunch of zeros. So we have sort of this triangular structure. Now, going back to example A, if I do a rotation about joint Q2, in which direction is this point PE moving? Left side up in this direction, and I'll make a note in a second that I don't know how long this arrow should be. Because the red arrow has a magnitude of 1, and this blue arrow you see here has a magnitude of, I think, 0.15. So they're not drawn to scale. But if I get some rotation about joint Q2, and this is, I think it was a little bit done clearer in the homework description, this would be a negative Q2, right? Positive Q2 is counterclockwise. So this is, once I have a positive Q2 dot, this point PE is moving this way. And we shouldn't forget about the 1 here, right? Because also the whole body is rotating exactly with the same velocity as q dot. So this gamma dot of sort of this body here is the same as q dot. That's why we have a 1 here. And then I could go ahead and read out these values, right? We did that in the past, where this and this both would exactly corresponds to this 1.1061. The lever arm between the rotation and the lateral motion of this point. So this would be this guy here. And then this, again, would be 0.1061, the lever arm between here and here, which would give me the vertical component of this blue arrow. Questions from your end? Good. Question from me? How many degrees of freedom do we have here? For the, let's say for the end effector, to be more specific, I'm just looking at the end effector, right? That's where I'm interested in. So I'm just looking at the bottom 3 rows of my Jacobian motion of the end effector. How many degrees of freedom? 2. How can you tell?
It has 2 directions to move. So you can move in the x-plane and xy plane. So
XY plane, right? You could argue we have 2 q dots, right? So that gives you 2 degrees of freedom. But we have to be very careful with both of these rationals because we can potentially run into singular configurations. So next question, can this robot run into a singular configuration where it cannot move in 2 directions anymore?
Yes, I think Q2 90 degrees.
If I do Q2 90 degrees, then a motion along Q1 is going to move me straight up. And the motion around Q2 is also going to move me straight up. What happens now is that sort of the lever arm for lateral motion becomes 0. And this lever arm would be is exactly 0.15. And my Jacobian, just the last 3 rows, would be 0, 1, 0. 0.15. And at this point, we think that the 2 are collinear. And if I just care about the position, I actually see that I ran into a... so if I would only care about the position, I would actually be in a kinematic singularity. Doesn't matter whether I move joint 1 or joint 2. This point is just moving up and down. So I can never go this way. Which kind of makes sense, right? Because there's no physical arm left to go this way. But since we're also interested in the position, in the orientation, not only in the position, but also in the orientation, I actually still have 2 degrees of freedom, right? Because I can independently influence 2 things. If I use Q1, I move up without rotation. If I use Q2, I move up while simultaneously rotate. And then you can imagine that I, at that sort of locally do a movement where I move Q1 down and Q2 up, and I can actually get a rotation without translating up or down, right? So again, mathematically, basically the best way of doing this, we look at the rank of this. Should we do the same thing for the second case, just a little bit quicker? But same idea. If I move Q1, everything is just going to translate upwards. This guy, and that guy. If I move joint Q2, P1 is not going to be influenced. Again, this triangular structure. P2 is moving similar to how PE moved before, with a slightly longer arrow, because we have here a longer lever arm, right? So this distance I think, is now 0.2. Sorry, the length is 0.2, but this distance would then be this 0.14, and here the same 0.14. And we kind of see, because that distance and that distance is the same, that means this Q2 is somewhere at 45 degrees. And here we have also a velocity 45 degrees towards the top left. What about point PE? Where is that moving? Or how do I construct the direction? Maybe that's the better question.
Linking P1 to PE and take a very different direction.
So that's important, right? We're now interested, we're still looking at this joint Q2, so I have to look at the joint center Q2 and think about how does PE rotate about this joint center Q2, and then I would get a vector something like this. In terms of numerical values, right, we thought about the Jacobian representing these lever arms. I have here, in terms of the vertical component, I always have this lever arm. And we see that for the vertical component, the lever arm of P2 and PE, those lever arms are the same. And so I would expect that this value and that value are the same. So if I rotate with some velocity Q2 dot down here, PE and P2 will move with exactly the same velocity upward, simply because they have the same lateral distance to the center of rotation. Question?
Yeah, it's also if Q4 is 0, we have the singularities here.
We get to the singularities in a second. I wanted to show that. The second thing that I wanted to show is that then, of course, for the x motion, here the value is much larger because this point PE is much higher above the center of rotation than P2. Right? So this 0.29 is basically 1.41, this distance plus this distance, d, and d in the example is 0.15. So 0.14 plus 0.15 gives me exactly this. So this will be, here would be the 0.29, and so on. If I move about joint 3, where does P1 go? Nowhere, right? Bunch of zeros. Is not influenced by the motion of Q3. Where does P2 go? If I now have a motion about joint Q3. This way. Where does PE go? Exactly same direction. Right? And these are now not lever arms in the traditional sense, but they are directions with of translational motion, so they have a magnitude of 1, which we don't see in this drawing because they're not drawn to scale. But we see here, right? They're basically 1 over square root 2, or square root 2, 1/2 square root 2 in both cases. And then lastly, we have a motion of joint Q4, where joint Q4 is not influencing P1, it's not influencing P2, but it's moving PE, the end effector, perfectly to the right, right? So no y component, negative minus 0.5 in the x direction, and then of course we have this rotational component. So those are the directions of motion that we see here. And again, I would be able to read off the lever arm directly from the figure. Motion to the right requires the horizontal lever arm, and that horizontal lever arm is equal to this constant small d, which is 0.15 in the question. Okay? How many degrees of freedom does the end effector have in this case, in case B? 4? That seems odd. In a planar system, having 4 degrees of freedom. 2? That's also odd. The end effector, right, has a position, 2 position, and 1 orientation. So at max, it can have 3. We have 4 joints. Now the question is, with these 4 joints, do we get all of these 3? And this is where I basically have to look at now at the bottom 3 rows of the Jacobian and look at their rank. Right? I have a 3×4 matrix. The number of degrees of freedom is the rank. What's the maximum rank a 3×4 matrix can have? 3. Right? It's always the smaller number. So maximally 3, in this case, independent columns. Now we have to check, are these indeed independent columns? And I think that's easy to do. If I look at the first and the last one, they're not only independent, but also orthogonal to each other. And then I see that this guy is also giving me sort of a direction that is neither collinear to this nor collinear to that. So we're good in this case, right? And then there's an extra Q that we don't need, right? That gives us some redundancy. So I have, in a sense, I have a null space motion. I can ask for x dot equals to 0. So end effector does not move, yet the rest of the robot can move, right? That's the definition of a null space. I can find some Q dot that will basically keep the end effector in place while changing some of the configuration down here. And you can kind of imagine how this will happen if I keep the end effector in place. I want to move this up. I have to tilt that down, contract that a little bit, and you can kind of imagine how I can move things around down here without influencing my end effector. Right? So of course, the entire system has 4 degrees of freedom, right? Because we have 4 Qs. But if I just think about the task space, so what is the end effector doing, I have just 3 of them. Now, same question. Can the end effector run into a kinematic singularity? So can you think of a configuration where I don't get 3 degrees of freedom for my end effector? That one would guess, but if everything's straight, I basically align these 2 with each other. So I'm losing, right? I'm losing a degree of freedom because Q1 and Q3 are doing the same. And then you would do 90 degrees here.
So it basically becomes similar to the previous one.
So Q4 would also point up. And in that case, my end effector, let me think, would still have 3 degrees of freedom because you would still have your Q2, right? So Q2 could move left and right, and Q4 could rotate. So you would get basically independent rotation, independent left, right, independent up and down. So the idea when you look for these singularities is to align joint axes, right? And here I align Q1 and Q3, and we would see that in the Jacobian, right? If this goes to 0, Q3 would point straight up, and the Jacobian would be 0, 1, 0, and those 2 would be collinear. And I'm basically losing some degree of freedom, or I could basically move point P1 up and down without changing anything up there. But it would not give me a full singularity because I still have these. Where I actually can get a full singularity is if I look at the point P2, right? If I place my end effector here, we already see, right? I'm in a little bit, I'm in worse shape to begin with because I only have 3 Qs. So if I align 2 joined axes, I will run into a singularity. So if I look at this, the middle 3 rows for this point P2, how would a singularity look like there? So you say Q1 and Q3 aligned. So here would be Q2, and I set this to basically 0 degrees. And here would be P2. And so I have Q1, Q2, Q3. And now we sort of see this redundancy that if I move Q1 and Q3 at the same time with different signs, I will just move this inner part up and down without moving P2. In other words, I get, if I move with Q1, I go this way. If I move with Q3, I get exactly the same motion. And then, as you said, right, if I move with Q2, I would get a motion in this direction directly coupled to a rotation. So I cannot independently control rotation and lateral motion. And even though I have 3 arrows, they just span a 2-dimensional space. So moving straight up or moving to the left while rotating by some amount. So here we really get a kinematic singularity, and we would see this numerically in this configuration, right? We would get here 0, 1, 0, and we would see that this column and that column are exactly the same. They're collinear. The rank of that matrix down here would just be 2, with 2 degrees of freedom left. That's all I wanted to show you here.